Welcome all to another lecture on CS403 Programming Paradigms. In this lecture, we'll be handling Module 2, where we talk about the type systems and the data types used in various languages. Myself, Mino Matthew. I'm an assistant professor in computer science and engineering at Rajagiri School of Engineering and Technology. This is the syllabus of Module 2. Here we talk about the data types, and then talk about what is type systems, type checking, and the various data structures that are used across languages. Before talking about type systems and type checking, let's see what is a data type. Any object that is used in the language is typable. The object may be a single variable or it may be an expression. An expression, when evaluated to a particular value, that value has a type or data type that is valid in the language. So there are two main purposes of a data type. The first one is implicit context for operations. If you have two numbers a and b, a plus b would indicate an integer addition if a and b were integers, and a plus b would be a float addition if a and b were float. And it limits the set of operations that may be performed in a valid program. For example, you cannot add an integer to a character or integer to a string. Okay, a plus b is only for numbers, and a and b must strictly be integers or strictly be float numbers. Also, if a particular subroutine is defined to get argument integer type, it will never be invoked with an argument of char or argument file. All those things are invalid. Type systems. Now, type system is a mechanism to define types and also a set of rules for defining what is type equivalence, type compatibility, and type inference. Now, let's see what are these. Now, type equivalence is to determine whether the types of two values are the same. And type compatibility is to see whether a particular value with a particular data type can be used in the current context. And type inference is when the type of an expression is not given, but it can be inferred from the surrounding context. Type checking is a process of ensuring that a program obeys the language's type compatibility rules. If there is a mismatch in type, it is called a type clash. Accordingly, the languages are categorized into two: strongly typed language and weakly typed languages. In strongly typed language, it prohibits the application of any operation on an object if it is not supported in the type system. And in a weakly typed language, the variables or objects are not bound to any particular data type. The examples for weakly typed languages are PHP and C. There are two other types of languages, statically typed language and dynamically typed language. In statically typed language, the binding happens during compile time, and in dynamically typed languages, the typing happens during the run time. It does not know the type until it is run. The example for statically typed language is Ada, and the example for dynamically typed language is Lisp and Smalltalk. And most of the scripting languages are also dynamically typed. And once it is typed, Python and Ruby maintains the type. I've put together the examples for dynamically typed languages and the statically typed languages into a nutshell. In dynamically typed languages, we have JavaScript, Lisp, PHP, Prolog, Python, Ruby, etc. And in statically typed, we have Ada, C, C++, C Sharp, Jade, Java, Fortran, ML, Pascal, etc. This is example code for static and dynamic. In static case, in Java, we have declared a variable foo of type string, and it is assigned the value hello world. This is static because we have assigned a foo as string, and it does not happen during runtime. Instead, it happens during the compile time. And in dynamic, the example is from Ruby, and the same variable foo is given hello world. Here, it is not explicitly mentioned string, but since it is dynamic, while running the line, it understands that foo is assigned a string because the assignment is a string. Then in case of weakly typed language, the same variable is first in PHP, the same variable foo is assigned x first, but in the very next line, 2 is added to it. We may expect an error, but since it is a weakly typed language, it will return 2 as the answer, meaning foo was assigned the type of int at runtime. Now let's talk about structural equivalence. In the slide you can see 3 different ways of defining a structure. This structure has 2 data members A and B, both of them are int. It appears to be the same. All the declarations are the same, but some languages does not allow the difference in the structure. Structure in the sense, in the first one you can see everything in one line. In the second one the braces are separated and the declarations come together. Declarations in the sense int A, B, all in the same line. A and B in the same line. Now in the third one, the structure is similar to the second one, but the data members are declared separately. Does this make a difference? Let's look into another example. In the slide you can see 2 variable declarations. In the first one, a variable called str is declared as a character array. In the first one, the index begins at 1, and the second one, the array begins at 0. That is a difference. So does it mean the same or is it different? And on the right you can see another example of a structure where there are only 2 members A and B, both of them are int, but the only difference is their order of declaration is different. It doesn't look different, but some languages like ML says it is not equivalent. Type equivalence. There are 2 ways of defining type equivalence. The first one is structural equivalence and the second one is name equivalence. In structural equivalence, as the name suggests, we look at the structure, that is the contents or the components of a type, and also the way in which it is expressed should be the same. That is, 2 types should have the same components put together in the same way, all in an exactly same way. And in case of name equivalence, it is very straightforward. 2 types are equivalent if they have the same names. Okay, but please don't misunderstand for defining a character array and an integer array under the same name, and we don't say that it is equivalent. Okay, we'll see examples for it. Let's look at an example for name equivalence. On the screen you can see 2 record types being defined. First one is student and the second one is school. In both student and school, there are 3 members, name, address and age, all of the same type in both school and student. And x is defined, the variable x is defined of type student and y is defined of type school. X equal to y will flag an error if it is a strict name equivalence, because it does not refer to the same type. Okay, if it was x comma y student, then x and y are of the same type. Okay, so it is name equivalence. And if it was x and y in school, x equal to y will hold true. Here are the examples for structural equivalence. In the first example, there is T1 and T2. It has 2 components A and B. A isn't, B is real. The components are the same and it is defined in the same manner, though the positions are exchanged. So it is a structural equivalence. And in the second example, there are 2 record types, student and school. Both student and school has name and address, both of them are string. It is defined in the same manner and it has the same components. So it is structurally equivalent, but name equivalence does not hold. In the third example, there is age and weight, both of them are float. Structurally it is equivalent, but name wise it is not. So one of the issues of structural equivalence is that we might assign age to weight or weight to age because both of them are float. Okay, such mistakes can happen. Let's see what happens when you encounter a value that was not expected in a particular context. That type of error is called a type error. You were expecting a particular data type, you got something else. So there are 3 ways of dealing with type errors. The first one is typecasting, where you explicitly change the type from one to another. Second one is type coercion, where it is implicit conversion, and the third one is non-converting typecast. Coming to the first type, it is a typecasting or the implicit typecasting. In implicit typecasting, the order in which it is converted is the hierarchical order starting from bool to long double. That is, you can implicitly, the system will implicitly convert a bool into char into short int, to int, so, and it goes on. Okay, and in case of float, it can be upgraded to double. Okay, now let's see what are the rules for typecasting. Type coercion. Type coercion is an automatic conversion of one type to another, and there are two conditions that has to be satisfied. The source and destination must be compatible, and the destination must be larger than the source. This is a widening conversion wherein a smaller data type will be converted to a larger one. According to the previous slide, we have seen a hierarchy of sizes where we've seen the int is smaller than float. In the example given, we have var1 as integer variable and var2 as float variable. We are assigning an integer value to a float variable. So we have to widen the destination. The destination is larger. The system will automatically convert the value 5 into a float value with 6 zeros after the decimal point. Here is another example of implicit type conversion. It is an example from C language. Here we have two variables, number and character. The number has value 1 and character has a value k. Can we add number and character together? Yes. The system will implicitly convert character into an integer. The ASCII value of character is 107. So when we add number and character, we'll get the value as 108. Moving on to the next type of conversion, typecasting. It is also called an explicit typecasting because this conversion is done only when explicitly stated by the programmer in the program. There are two conditions that has to be satisfied. The first condition, the source and destination are not compatible, and the destination is smaller than the source. So the system cannot automatically convert it to a new data type. For example, there are two variables, number and fval. Fval has the value 32.33. If this value has to be stored in an integer variable, it has to be converted to an integer. So the programmer has to explicitly state in the program that the variable fval has to be explicitly converted to int and store the value in number. Now let's compare implicit and explicit type conversions in a single slide. On the left hand side you can see the example for implicit conversion, and on the right hand side you can see the explicit type conversion. Now let's begin with the implicit conversion. Here we have two variables x and y. X is int and y is char. So if we add x and y, the ASCII value of a will be added to the number 10. So what happens? 97 plus 10 will give you 107 as the value of x, and z is equal to x plus 1.0. So x is int now. Since it is the conversion to a higher data type, it is done automatically, and the result is 107 and 108.0000. How the type conversion has happened here. Okay, implicit type conversion has happened. Now in case of the right hand side, there is a variable x which is of double data type, and its value is 1.2. If we want to add 1 to it and store it into an integer variable, we have to explicitly state that x has to be converted to integer and then add 1 to it. So the result would be 2. Coming to the third type of type conversion, it is a non-converting typecast. It is also called type 1, where we do not change the implementation. We simply interpret the value of one type as another type. For example, an array of byte is represented as a heap, and each individual element on the heap can be interpreted as pointers or integers or even other user-defined data types. These are the three functions that are used in C++ for type conversion. The static cast performs the static type conversion, and reinterpret cast performs non-converting typecast. Dynamic cast is used for polymorphic types at runtime. Now let's talk about another interesting feature of languages, orthogonality. In a highly orthogonal language, the features can be used in any combination. This will make the language very flexible. It will be easier to understand, easier to use, and we have different combinations of it. For example, in the given example, there is a function insert in symbol table. The same function has been called in two places in the program. In the first position, it returns a value, and in the second position it does not return a value, instead it returns the empty type. So it means the same function has been used in two contexts. For the previous example, if the language does not support a void data type, the return type is taken into a dummy variable. So dummy is the dummy variable, and insert in symbol table will return a value that is taken into the dummy variable. The type system of C and Pascal are more orthogonal than that of Fortran. The array elements in Fortran is always scalar, but C and Pascal allows arbitrary types. The array index in Pascal can be discrete, but integers are only allowed in C. In Pascal, the function returns value as scalars, and in C it allows structures and pointers to functions. We can interpret the meaning of type in three ways. There are 3 points of view. The first one is denotational, that is, type is simply a set of values. We are not concerned about the different ways in which it can be represented. And in constructive point of view, type is either one of the smaller collection of built-in types, integer, character, boolean, real, etc., or it is a composite type. Either it is a built-in type or a composite type. And in abstract point of view, type is an interface consisting of a set of operations with well-defined and mutually consistent semantics. The last one, the abstraction view, is much desired. Classification of types. The data types that are available can be classified into 6 types: booleans, characters, numeric type, enumeration, subrange, and composite type. We have to deal with the composite type in detail, so we'll be checking out what are the first 5. Classification of types. First one is built-in data type: boolean, character, integer, and float. These built-in data types are available across languages. Now, character is a 1 byte quantity. It is usually the ASCII code or the unique code of a character. And the other numeric types that are available are complex numbers, rational numbers, signed and unsigned integers, floating point numbers. And also in some languages, the numeric type can have a precision, that is single or double precision numbers. Okay, integer as 4 bytes and long as 8 bytes. Enumeration is a user-defined data type that was introduced in Pascal, and it was used for improving the program readability and error checking. For example, in Pascal, weekday is the type weekday can take the values Sunday, Monday, Tuesday, Wednesday, Thursday, etc. up to Saturday. Now this will allow the arrays to use these values Sunday, Monday, Tuesday, etc. as array index. It will give a much meaningful program. When the programmer reads through the program, it would be much more easier. The same feature is available in C, where enum is the keyword that is used for declaring enumeration, and we can use the enum data type with switch case. Subranges. It is a user-defined ordinal type which was used for improving the program readability and error checking. This was also first introduced in Pascal, and in Pascal you can see the examples. The test score is an integer number between 0 and 100, and work day is Monday to Friday, where the weekday is from Sunday to Saturday. And type in ADA, type test score is a new integer in the range 0 to 100, and subtype workday is a weekday in the range Monday to Friday. Now test score is a derived type and work day is a constrained subtype, where we have already a type weekday and work day is a subtype of it. More examples of subranges from Python. Here the subrange is defined from 1 to 5 and it is defined under the name R. So when we print R, 1 to 5 will be printed. The whole subrange will be printed, and r.min and r.max will print the maximum and min among the subrange. Then print 4 in R. It will return true because 4 is there in the subrange. Then for print I for I in R, that is for each and every I, each and every value in R will be printed. Print R less than 6. Yes, it is true and true will be printed on the screen. Thank you for your patient listening. We have come to the end of part 1 of module 2. We'll continue with the second part in the next presentation.